Fundamental theorem of algebra. The fundamental theorem of algebra, also known as D'Alembert's theorem, or the D'Alembert-Gauss theorem, states that every non-constant single-variable polynomial with complex coefficients has at least one complex root. This includes polynomials with real coefficients, since every real number is a complex number with its imaginary part equal to 0. Equivalently, by definition, the theorem states that the field of complex numbers is algebraically closed. The theorem is also stated as follows: every non-zero, single-variable, degree n polynomial with complex coefficients has counted with multiplicity exactly n complex roots. The equivalence of the two statements can be proven through the use of successive polynomial division. Despite its name, there is no purely algebraic proof of the theorem, since any proof must use some form of the analytic completeness of the real numbers, which is not an algebraic concept. Additionally, it is not fundamental for modern algebra. Its name was given at a time when algebra was synonymous with theory of equations. History. Peter Roth, in his book Arithmetica Philosophica published in 1608 at Nuremberg by Johann Latzenberger, wrote that a polynomial equation of degree n with real coefficients may have n solutions. Albert Gerard, in his book L'Invention nouvelle en l'algèbre published in 1629, asserted that a polynomial equation of degree n has n solutions, but he did not state that they had to be real numbers. Furthermore, he added that his assertion holds unless the equation is incomplete, by which he meant that no coefficient is equal to 0. However, when he explains in detail what he means, it is clear that he actually believes that his assertion is always true. For instance, he shows that the equation x4 equals 4x minus 3, although incomplete, has 4 solutions counting multiplicities 1 twice, $-1 plus I backslash sqrt2 and $-1 I backslash sqrt2. As will be mentioned again below, it follows from the fundamental theorem of algebra that every non-constant polynomial with real coefficients can be written as a product of polynomials with real coefficients whose degrees are either 1 or 2. However, in 1702 Leibniz erroneously said that no polynomial of the type with real and distinct from 0 can be written in such a way. Later, Nicolas Bernoulli made the same assertion concerning the polynomial, but he got a letter from Euler in 1742 in which it was shown that this polynomial is equal to $backslash left x to 2 plus backslash alpha x plus 1 plus backslash sqrt7 plus backslash alpha. I backslash left x to 2 backslash alpha x plus 1 plus backslash sqrt7 backslash alpha. I $$ with $$ backslash alpha equals backslash sqrt4 plus 2 backslash sqrt7. Also, Euler pointed out that $x4 plus f4 equals backslash left x2 plus a backslash sqrt2 backslash c dot x plus a 2. I backslash left x2 a backslash sqrt2 backslash c dot x plus a 2. A first attempt at proving the theorem was made by D'Alembert in 1746, but his proof was incomplete. Among other problems, it assumed implicitly a theorem now known as Puiseux's theorem, which would not be proved until more than a century later and using a fundamental theorem of algebra. Other attempts were made by Euler 1749, de Fontenay 1759, Lagrange 1772, and Laplace 1795. These last 4 attempts assumed implicitly Gerard's assertion. To be more precise, the existence of solutions was assumed and all that remained to be proved was that their form was a plus by for some real numbers a and b. In modern terms, Euler, de Fontenay, Lagrange, and Laplace were assuming the existence of a splitting field of the polynomial Pz. At the end of the 18th century, 2 new proofs were published which did not assume the existence of roots, but neither of which was complete. One of them, due to James Wood and mainly algebraic, was published in 1798 and it was totally ignored. Wood's proof had an algebraic gap. The other one was published by Gauss in 1799 and it was mainly geometric, but it had a topological gap only filled by Alexander Ostrowski in 1920 as discussed in Smale 1981. The first rigorous proof was published by Argand, an amateur mathematician, in 1806 and revisited in 1813. It was also here that, for the first time, the fundamental theorem of algebra was stated for polynomials with complex coefficients, rather than just real coefficients. Gauss produced 2 other proofs in 1816 and another incomplete version of his original proof in 1849. The first textbook containing a proof of the theorem was Koch's d'analyse de l'école Royale Polytechnique 1821. It contained Argand's proof, although Argand is not credited for it. None of the proofs mentioned so far is constructive. It was Weierstrass who raised for the first time, in the middle of the 19th century, the problem of finding a constructive proof of the fundamental theorem of algebra. He presented his solution, which amounts in modern terms to a combination of the Durand-Kerner method with the homotopy continuation principle in 1891. Another proof of this kind was obtained by Helmuth Nesser in 1940 and simplified by his son Martin Nesser in 1981. Without using countable choice, it is not possible to constructively prove the fundamental theorem of algebra for complex numbers based on the Dedekind real numbers which are not constructively equivalent to the Cauchy real numbers without countable choice. However, Fred Richman proved a reformulated version of the theorem that does work. Equivalent statements. There are several equivalent formulations of the theorem. Every univariate polynomial of positive degree with real coefficients has at least one complex root. Every univariate polynomial of positive degree with complex coefficients has at least one complex root. This implies immediately the previous assertion, as real numbers are also complex numbers. The converse results from the fact that one gets a polynomial with real coefficients by taking the product of a polynomial and its complex conjugate obtained by replacing each coefficient with its complex conjugate. A root of this product is either a root of the given polynomial or of its conjugate. In the latter case, the conjugate of this root is a root of the given polynomial. Every univariate polynomial of positive degree with complex coefficients can be factorized as Cx minus Rx minus Rn, where C, R, Rn are complex numbers. The complex numbers R, Rn are the roots of the polynomial. If a root appears in several factors, it is a multiple root, and the number of its occurrences is, by definition, the multiplicity of the root. The proof that this statement results from the previous ones is done by recursion on. When a root R1 has been found, the polynomial division by x minus R1 provides a polynomial of degree n minus 1 whose roots are the other roots of the given polynomial. The next two statements are equivalent to the previous ones, although they do not involve any non-real complex number. These statements can be proved from previous factorizations by remarking that, if is a non-real root of a polynomial with real coefficients, its complex conjugate $\overline $r$ is also a root, and $xrx $\overline $r$ is a polynomial of degree 2 with real coefficients. Conversely, if one has a factor of degree 2, the quadratic formula gives a root. Every univariate polynomial with real coefficients of degree larger than 2 has a factor of degree 2 with real coefficients. Every univariate polynomial with real coefficients of positive degree can be factored as CPPK, where is a real number and each pi is a monic polynomial of degree at most 2 with real coefficients. Moreover, one can suppose that the factors of degree 2 do not have any real root. Proofs. All proofs below involve some mathematical analysis, or at least the topological concept of continuity of real or complex functions. Some also use differentiable or even analytic functions. This requirement has led to the remark that the fundamental theorem of algebra is neither fundamental nor a theorem of algebra. Some proofs of the theorem only prove that any non-constant polynomial with real coefficients has some complex root. This lemma is enough to establish the general case because, given a non-constant polynomial pz with complex coefficients, the polynomial $qz equals pz \overline p \overline z $. Has only real coefficients, and, if z is a zero of qz, then either z or its conjugate is a root of pz. Many non-algebraic proofs of the theorem use the fact sometimes called the Grove lemma that a polynomial function pz of degree n whose dominant coefficient is 1 behaves like zm when z is large enough. More precisely, there is some positive real number r such that $t frac 1 2z mpz \t frac 3 2z n when z r real analytic proofs. Even without using complex numbers, it is possible to show that a real-valued polynomial px p0 not equal to 0 degree n2 can always be divided by some quadratic polynomial with real coefficients. In other words, for some real valued at nb, the coefficients of the linear remainder on dividing px by x2 minus x minus b simultaneously become 0. Px equals x2 minus x minus bqx plus xr pxa b plus spxa b, where qx is a polynomial of degree n minus 2. The coefficients rpxa b and spxa b are independent of x and completely defined by the coefficients of px. In terms of representation, rpxa b and spxa b are bivariate polynomials in A and B. In the flavor of Gauss's first and complete proof of this theorem from 1799, the key is to show that for any sufficiently large negative value of b, all the roots of both rpxa b and spxa b in the variable are real valued and alternating each other in delacing property. Utilizing a stem-like chain that contain RPXAB and SPXAB as consecutive terms, interlacing in the variable it can be shown for all consecutive pairs in the chain whenever b is sufficiently large negative value. As S par b equals 0 equal p0 has no roots, interlacing of RPXAB and SPXAB in a variable fails at b equals 0. Topological arguments can be applied on the interlacing property to show that the locus of the roots of RPXAB and SPXAB must intersect for some real value to n be 0. Complex analytic proofs. Find a closed disk d of radius r centered at the origin such that p0 whenever z greater or equal to r. The minimum of pz on d, which must exist since d is compact, is therefore achieved at some point c0 in the interior of d, but not at any point of its boundary. The maximum modulus principle applied to 1/pz implies that pz0 equals 0. In other words, c0 is a 0 of pz. A variation of this proof does not require the maximum modulus principle. In fact, a similar argument also gives a proof of the maximum modulus principle for holomorphic functions. Continuing from before the principle was invoked, if a equals pz0 not equal to 0, then expanding pz in powers of z minus c, we can write pz equals a plus ckz minus ck plus ck plus 1s minus ck plus 1 plus cnz minus cn. Here, the c, j are simply the coefficients of the polynomial z right arrow pz plus c0 after expansion, and k is the index of the first non-zero coefficient following the constant term. For z sufficiently close to z0, this function has behavior asymptotically similar to the simpler polynomial qz equals a plus ckz minus ck. More precisely, the function $left frac bz qz z0 k plus 1 height like m for some positive constant m in some neighborhood of z. Therefore, if we define θ0 equals alga plus pi minus arg ck/k and let z equals c0 plus re θ0 tracing a circle of radius r0 around z, then for any sufficiently small r so that the bound m holds, we see that begin a line pz and a qz plus rk plus 1 left frac pz qz rk plus 1 I and left plus minus 1 k rk ei org k I plus m rk plus 1 n equals a c k rk plus m rk plus 1 and a line When r is sufficiently close to 0, this upper bound for pz is strictly smaller than a, contradicting the definition of z. Geometrically, we have found an explicit direction θ0 such that if one approaches z0 from the direction, one can obtain values pz smaller in absolute value than pz. Another analytic proof can be obtained along this line of thought, observing that, since p0 outside d, the minimum of pz on the whole complex plane is achieved at z. If pz 0, then 1/p is a bounded holomorphic function in the entire complex plane, since, for each complex number z, 1/pz less or equal to 1/pz. Applying Liouville's theorem, which states that a bounded entire function must be constant, this would imply that 1/p is constant, and therefore that p is constant. This gives a contradiction, and hence pz0 equals 0. Yet another analytic proof uses the argument principle. Let r be a positive real number large enough so that every root of pz has absolute value smaller than r. Such a number must exist because every non-constant polynomial function of degree n has at most n zeros. For each r, consider the number $frac 1 2 pi I /ncr frac pz $dz where cr is the circle centered at 0 with radius r oriented counterclockwise. Then the argument principle says that this number is the number north of zeros of pz in the open ball centered at 0 with radius r, which, since r is the total number of zeros of pz. On the other hand, the integral of n/c along cr divided by 2 pi is equal to n. But the difference between the two numbers is $frac 1 2 pi I /ncr left frac pz frac nc I equals frac 1 2 pi I /ncr frac cpz and pz dz. The numerator of the rational expression being integrated has degree at most n-1, and the degree of the denominator is n plus 1. Therefore, the number above tends to 0 is r right arrow plus infinity. But the number is also equal to n-n, and so n equals n. Another complex analytic proof can be given by combining linear algebra with the Cauchy theorem. To establish that every complex polynomial of degree n0 has a 0, it suffices to show that every complex square matrix of size n0 has a complex eigenvalue. The proof of the latter statement is by contradiction. Let be a complex square matrix of size n0 and let IM be the unit matrix of the same size. Assume it has no eigenvalues. Consider the resolvent function Rz equals zin minus a minus 1, which is a meromorphic function on the complex plane with values in a vector space of matrices. The eigenvalues of R are precisely the poles of Rz. Since, by assumption, R has no eigenvalues, the function Rz is an entire function, and Cauchy theorem implies that integral CR Rz dz equals 0. On the other hand, Rz expanded as a geometric series gives $Rz equals z minus 1 in z minus 1 a minus 1 equals z minus 1 backslash sum k equals 0 backslash inf die backslash frac 1 z k a k backslash c dot $. This formula is valid outside the closed disk radius of the operator norm of a. Let R then $backslash int cr rdz equals backslash sum k equals 0 backslash inf die backslash in cr backslash frac dz k plus 1 a k equals 2 backslash pi I a n $, in which only the sum in k equals 0 has a non-zero integral. This is a contradiction, and so has an eigenvalue. Finally, Roche's theorem gives perhaps the shortest proof of the theorem. Topological proofs. Suppose a minimum of Pz on the whole complex plane is achieved at Z. It was seen at the proof which uses Liouville's theorem that such a number must exist. We can write Pz as a polynomial in Z minus C. There is some natural number k, and there are some complex numbers ck plus 1, Cn such that ck not equal to 0, and Pz equals Pz0 plus ckz minus ck plus ck plus 1's minus ck plus 1 plus Cnz minus Cn. If Pz0 is non-zero, it follows that if it is a kth root of minus Pz slash ck, and if t is positive and sufficiently small, then Pz0 plus top Pz, which is impossible since Pz is the minimum of P on D. For another topological proof by contradiction, suppose that the polynomial Pz has no roots and consequently is never equal to 0. Think of the polynomial as a map from the complex plane into the complex plane. It maps any circle Z equals R into a closed loop, a curve BR. We will consider what happens to the winding number of PR at the extremes when R is very large and when R equals 0. When R is a sufficiently large number, then the leading term Zn of Pz dominates all other terms combined. In other words, Cn n minus 1's n minus 1 plus busso. When Z traverses the circle re theta once counterclockwise 0 less or equal to theta less or equal to 2 pi, then Zn equals R ni and theta wins n times counterclockwise 0 less or equal to theta less or equal to 2 pi and around the origin 0, and PR likewise. At the other extreme, with Z equals 0, the curve P0 is merely the single point P0, which must be non-zero because Pz is never 0. Thus P0 must be distinct from the origin 0, which denotes 0 in the complex plane. The winding number of P0 around the origin 0 is thus 0. Now changing R continuously will deform the loop continuously. At some R the winding number must change. But that can only happen if the curve PR includes the origin 0 for some R, but then for some Z on the circle Z equals R we have Pz equals 0, contradicting our original assumption. Therefore Pz has at least one 0. Algebraic proofs. These proofs of the fundamental theorem of algebra must make use of the following two facts about real numbers that are not algebraic but require only a small amount of analysis. More precisely, the intermediate value theorem. In both cases, every polynomial with an odd degree and real coefficients has some real root. Every non-negative real number has a square root. The second fact, together with the quadratic formula, implies a theorem for real quadratic polynomials. In other words, algebraic proofs of the fundamental theorem actually show that if R is any real closed field, then its extensions L equal R is algebraically closed. By induction. As mentioned above, it suffices to check the statement every non-constant polynomial Pz with real coefficients has a complex root. This statement can be proved by induction on the greatest non-negative integer k such that 2k derives the degree n of Pz. Let it be the coefficient of Zn and Pz, and let Fahrenheit be a splitting field of Pz over C. In other words, the field Fahrenheit contains Celsius, and there are elements C, Cn and Fahrenheit such that Pz equals as minus C1 Z minus Cz minus Cn. If k equals 0, then n is odd, and therefore Pz has a real root. Now suppose that n equals 2km with meters odd and k0, and that the theorem is already proved when the degree of the polynomial has the form 2k minus 1 with m odd. For a real number t, define qtz equals 1 less or equal to ij less or equal to nc minus c, I minus c, j minus tz, oath, j. Then the coefficients of qtz are symmetric polynomials in the z, I with real coefficients. Therefore, they can be expressed as polynomials with real coefficients in the elementary symmetric polynomials, that is, in minus I, minus 1 na n. So qtz is in fact real coefficients. Furthermore, the degree of qtz is nn minus 1 / 2 equals 2k minus 1, and mn minus 1 is an odd number. So, using the induction hypothesis, qt has at least one complex root, in other words, z, I plus z, j plus tz. If j is complex for two distinct elements I and j from 1, n. Since there are more real numbers than pairs I, j, one can find distinct real numbers t and s such that z, I plus z, j plus tz, if j and z, I plus z, j plus sc, if j are complex for the same I and j. So both c, I plus c, j and z, if j are complex numbers. It is easy to check that every complex number has a complex square root, thus every complex polynomial of degree 2 has a complex root by the quadratic formula. It follows that c, I and z, j are complex numbers since they are roots of the quadratic polynomial z2 minus z, I plus z, z plus z, if j. Joseph Shipman showed in 2007 that the assumption that odd-degree polynomials have roots is stronger than necessary. Any field in which polynomials of prime degree have roots is algebraically closed, so odd can be replaced by odd prime, and this holds for fields of all characteristics. For axiomatization of algebraically closed fields, this is the best possible, as there are counterexamples if a single prime is excluded. However, these counterexamples rely on -1 having a square root. If we take a field where -1 has no square root, and every polynomial of degree n I is a root where is any fixed infinite set of odd numbers, then every polynomial fx of odd degree is a root since is a root where k is chosen, so that Mohsen al-Abadi generalized Shipman's result in 2013, providing an independent proof that a sufficient condition for an arbitrary field of any characteristic to be algebraically closed is that it has a root for every polynomial of prime degree. From Galois theory. Another algebraic proof of the fundamental theorem can be given using Galois theory. It suffices to show that Celsius has no proper finite field extension. Let k/c be a finite extension. Since the normal closure of Kelvin over R still is a finite degree over Celsius R, we may assume without loss of generality that Kelvin is a normal extension of R, hence it is a Galois extension, as every algebraic extension of a field of characteristic 0 is separable. Let G be the Galois group of this extension, and let H be a Sylow 2 subgroup of G, so that the order of H is a power of 2, and the index of H in G is odd. By the fundamental theorem of Galois theory, there exists a subextension L of k/R such that gal k/L equals H, as equals is odd, and there are no nonlinear reducible real polynomials of odd degree. We must have L equals R, thus n are powers of 2. Assuming by way of contradiction at 1, we conclude that the 2 group gal k/C contains a subgroup of index 2, so there exists a subextension M of Celsius of degree 2. However, Celsius has no extension of degree 2 because every quadratic complex polynomial has a complex root, as mentioned above. It shows that equal 1, and therefore Kelvin equals C, which completes the proof. Geometric proofs. There exists still another way to approach the fundamental theorem of algebra due to J. M. Almira and Romero by Riemannian geometric arguments. The main idea here is to prove that the existence of a non-constant polynomial Pz without zeros implies the existence of a flat Riemannian metric over the sphere S2. This leads to a contradiction since the sphere is not flat. A Riemannian surface M, G is said to be flat if its Gaussian curvature, which we denote by Kg, is identically null. Now, the Gauss-Bonnet theorem, when applied to the sphere S2, claims that integral S2 Kg equals 4 pi, which proves that the sphere is not flat. Let us now assume that n0 and Pz equals a 0 plus a 1z plus nz n not equal to 0. For each complex number z, let us define $P asterisk z equals z n p backslash left backslash t frac 1 z. It equal 0 z n plus a 1 z n minus 1 plus backslash c dots plus n. $. Obviously, p asterisk z not equal to 0 for all z in Celsius. Consider the polynomial fz equals pzp asterisk z. Then fz not equal to 0 for each c in Celsius. Furthermore, $f backslash t frac 1 w equal p backslash left backslash t frac 1 w. It asterisk backslash left backslash t frac 1 w. It equal w minus 1 p asterisk w p w equal w minus 1 f w. $. We can use this functional equation to prove that g given by $g equals backslash frac 1 fw backslash frac 2 n backslash dw 2 for w and c and $g equals backslash frac 1 backslash left f backslash left backslash t frac 1 w. It backslash frac 2 n backslash left d backslash left backslash t frac 1 w. It $. For w s2 backslash 0 is a well-defined Riemannian metric over the sphere S2 which we identify with the extended complex plane C infinity. Now a simple computation shows that $backslash 4 will w backslash n backslash math c backslash q quad backslash frac 1 fw backslash frac 1 n kg equals backslash frac 1 n backslash delta backslash log fw equals backslash frac 1 n backslash delta backslash x3 backslash log fw equals 0 $. Since the real part of an analytic function is harmonic, this proves that kg equals 0. Corollaries. Since the fundamental theorem of algebra can be seen as the statement that the field of complex numbers is algebraically closed, it follows that any theorem concerning algebraically closed fields applies to the field of complex numbers. Here are a few more consequences of the theorem, which are either about the field of real numbers or the relationship between the field of real numbers and the field of complex numbers. The field of complex numbers is the algebraic closure of the field of real numbers. Every polynomial in one variable z with complex coefficients is the product of a complex constant and polynomials of the form z plus a with a complex. Every polynomial in one variable x with real coefficients can be uniquely written as the product of a constant, polynomials of the form x plus a with the real, and polynomials of the form x2 plus x plus b with a and b real and a 2 minus 4 0, which is the same thing as saying that the polynomial x2 plus x plus b has no real roots. By the Abel-Ruffini theorem, the real numbers a and b are not necessarily expressible in terms of the coefficients of the polynomial, the basic arithmetic operations, and the extraction of nth roots. This implies that the number of non-real complex roots is always even and remains even when counted with their multiplicity. Every rational function in one variable x with real coefficients can be written as the sum of a polynomial function with rational functions of the form /x minus b n where n is a natural number and n b are real numbers, and rational functions of the form x plus b /x2 plus cx plus dn where n is a natural number and a, b, c, and d are real numbers such that c2 minus 4 0. A corollary of this is that every rational function in one variable and real coefficients has an elementary primitive. Every algebraic extension of the real field is isomorphic either to the real field or to the complex field. Bounds on the zeros of a polynomial. While the fundamental theorem of algebra states a general existence result, it is of some interest, both from the theoretical and from the practical point of view, to have information on the location of the zeros of a given polynomial. The simpler result in this direction is a bound on the modulus. All zeros z of a monic polynomial z n plus a n minus 1 z minus 1 plus a 1 z plus a 0 satisfy an inequality z less or equal to r infinity, where r infinity equals 1 plus max a n minus 1. Notice that, as stated, this is not yet an existence result but rather an example of what is called an a priori bound. It says that if there are solutions then they lie inside the closed disk of center, the origin and radius r infinity. However, once coupled with the fundamental theorem of algebra, it says that the disk contains in fact at least one solution. More generally, a bound can be given directly in terms of any p-norm of the n-vector of coefficients that equals a n minus 1, that is z less or equal to rp, where rp is precisely the q-norm of the two-vector 1 p, q being the conjugate exponent of p, $t frac 1 p plus d frac 1 q equals 1, $ for any 1 less or equal to p less or equal to infinity. Thus, the modulus of any solution is also bounded by it. R equals max 1 summation 0 less or equal to k and a k. $rp equals backslash left backslash frac 1 q $. For 1p infinity, and in particular, $r2 equals backslash sqrt backslash sum 0 backslash let k backslash let and a k $2, where we define n to mean 1, which is reasonable since 1 is indeed the nth coefficient of our polynomial. The case of a generic polynomial of degree n. Pz equals a ncn plus a n minus 1's n minus 1 plus a 1z plus a is of course reduced to the case of harmonic dividing all coefficients by n not equal to 0. Also, in case that 0 is not a root, that is a 0 not equal to 0, bounds from below on the root c to follow immediately as bounds from above on $backslash t frac 1 backslash zeta $, that is the roots of a 0 zn plus a 1 zn minus 1 plus a n minus 1 plus n. Finally, the distance zeta minus zeta from the root zeta to any point zeta 0 can be estimated from below and above, seeing zeta minus zeta 0 as zeros of the polynomial pz plus zeta, whose coefficients are the Taylor expansion of pz at z equals zeta. Let zeta be a root of the polynomial cn plus a n minus 1's n minus 1 plus a 1z plus a. In order to prove the inequality zeta less or equal to rp, we can assume, of course, zeta 1. Writing the equation as minus zeta n equals a n minus 1 zeta n minus 1 plus a 1 zeta plus a. And using the Hölder's inequality, we find zeta n less or equal to p zeta n minus 1 theta 1 q. Now, if p equal 1, this is zeta n less or equal to a max zeta n minus 1, zeta 1 equals a zeta n minus 1. Thus, zeta less or equal to max 1 a. In the case 1p less or equal to infinity, taking into account the summation formula for a geometric progression, we have $backslash zeta n backslash let backslash a backslash p backslash left backslash zeta qn minus 1 plus backslash c dots plus backslash zeta q plus 1. It backslash frac 1 q equals backslash a backslash p backslash left backslash frac backslash zeta qn minus 1 backslash zeta q minus 1. It backslash frac 1 q backslash let backslash a backslash p backslash left backslash frac backslash zeta qn backslash zeta q minus 1. It backslash frac 1 q $. Thus, $backslash zeta nq backslash let backslash a backslash pq backslash frac backslash zeta qn backslash zeta q minus $1. And simplifying, zeta q less or equal to 1 plus a p q. Therefore, zeta less or equal to 1 a p q equals r p holds for all 1 less or equal to p less or equal to infinity. Historic sources: TR Course on Analysis of the Royal Polytechnic Academy, Part 1, Algebraic Analysis. English translation: TR New proof of the theorem that every integral rational algebraic function of one variable can be resolved into real factors of the first or second degree. 1. First proof. 2. Second proof. 3. Third proof. 4. Fourth proof. The fundamental theorem of algebra and intuitionism. TR, an extension of a work of Helmuth Nisser and the fundamental theorem of algebra. TR, and the first and fourth Gaussian proofs of the fundamental theorem of algebra. TR, new proof of the theorem that every integral rational function of one variable can be represented as a product of linear functions of the same variable. Recent literature. TR, and the history of the fundamental theorem of algebra, theory of equations in integral calculus. TR, the rational functions, section 8088, the fundamental theorem, one English translation of Gauss's second proof.